Okay, folks, next learning goal, this will be another short one. Know how to determine the relative rate of each species in a chemical reaction. Okay, so let's see here. So to set this up, I've got a real reaction here that we're looking at instead of our generic reactions. And so this is the reaction of two NO radicals reacting with O2 to form two NO2 radicals. And if we were to look at concentration versus time, we can see that the NO and the O2 decay at some certain rate, and the NO2 evolves at some certain rate. And if we look at this tangential point here that this figure is showing you, right, like delta O2 over delta time, we can see that all of these rates are different. So for example, the rate of consumption of O2 has a slope that looks like that. And hopefully maybe what you can infer, the rate of NO is twice as steep as the rate of O2. And this is really difficult to tell, but the rate of evolution of NO2 is the same as the rate of decay of NO, just equal and opposite. So how do we get to that? How do we see those relative rates between each species? Well, if we take advantage here of that definition with 1 over the stoichiometric coefficient, we will see just that. Okay, so for example, let's start plugging all of this in. So we'll write that the stoichiometric coefficient for NO, let's do the reactants first, is -2. The stoichiometric coefficient for O2 is -1. And the stoichiometric coefficient for NO2 is +2. So now as we set all of these rates up, we can do the following. So for NO, that's going to be -1/2, right? 1 over -2. And that's going to be dNO over dt. Well, we can set that equal to the next rate when we consider the stoichiometric coefficient. So for O2, the stoichiometric coefficient was just -1, so that's going to be -dO2 dt. And then now we can finally do the same thing for NO, noting that it's +2, so now that becomes +1/2 dNO2 dt. And so now, as we were discussing this earlier, right, we said that the rate of decay of NO was the same as the rate of evolution of NO2, but they were just opposite in sign. And we could see just that, -1/2 dNO dt equals +1/2 dNO2 dt. And then similarly, in order to make the rates of O2 and NO equal to each other, because NO is decaying at a rate twice that of O2, if we divide the rate of NO by 1/2, it will equal the rate of O2. So this is what I mean when we say our relative reaction rates. Okay. So, and then of course, if we were to plug in actual values to calculate those deltas, we would then all get equivalent numbers when considering their stoichiometric coefficients. All right, that's all that I wanted to say about this learning goal. I'll see you in the next one.